Hi, welcome back. This is the physics of martial arts. This is part 2. In this part, I will be talking about the effects of rotational mechanics. In this section, I will cover a range of issues dealing with the use of rotational mechanics, mostly with the idea of rigid body motion. The body, when performing the martial arts, is used in various ways to improve balance, speed, and overall power as a system. To perfect this use of the entire body can take years of practical application, but only moments to understand. So first, let us discuss the different ways that the body moves when performing certain attacks or blocks in the martial arts. For our purposes now, we will only take into account the hard style art movements. Many of the hard style and soft style movements are similar and rightly so, being based on a single base system which has been diversified and refined throughout thousands of years. We will focus on the hard style system first. So with the punches that we discussed previously, there comes much more motion from the body. First, there is rotational motion at the hips, that thus causing the upper half of the body to turn, the shoulders to extend, and the arm to gain distance so that it can accelerate through the target. This motion will add a large amount of energy and momentum to the movement of the previously simple punch. We will estimate the shape of the human torso to be equivalent to these figures over here. Now, this is figure 1, and this one would be figure number 2. And I will tell you what each figure is. The first figure is a two-dimensional approximation of the shape of the human torso from the front perspective. And the second part of the figure is how we will approximate the shape as a three-dimensional version of the first part of the figure. For that shape, we will approximate the moment of inertia, I, to be that of a thin white rectangle, where I equals 1 over 12 m brackets w squared plus d squared, where m is the mass of the torso, w is the distance from the center of the torso to this edge of the shoulder, and d is the distance from the center of the torso to the outer edge of the back. So let's use the following actual values for each of these variables, which would be m equals 35 kilograms, w is 22 centimeters, which converted is 0.22 meters, d is 7 centimeters, converted is 0.07 meters. I'm sorry, I don't know if I said 7 centimeters or meters by mistake, but what I meant is 7 centimeters, converted is 0.07 meters. So having these three numbers, you can just convert them all into this equation and you will get I. And having I, you have enough information to be able to get new values of energy, force, and pressure for the linear punch, adding the effects of the rotational mechanics of the body to these equations as well. But I won't be going into the pressure and the force one, because I've already done the force in the last video and the pressure one. It's just that rotational mechanic will just be added to it, but we haven't done energy. That's why I'm just going to do energy with the variables that we have, with the values that we have for these variables. So energy is, this is the formula for energy. All we have to do is to sub them in. This is what we're going to get, and when you just use your calculator, you're going to get this for an answer. E equals 207.03 joules. Joules is for energy. That's why we use it. Now, knowing all this, I didn't do the punch and the pressure and the force, like I didn't do the pressure of the punch and the force of the punch, but we can tell that the mechanical energy is twice as much than if there was no rotational move, because this proves that adding rotational mechanics into the linear movement can increase the energy output drastically, allowing for a much more destructive and powerful strike. Alright, now before we get into rotational mechanics where people grab each other and take down and do judo, as you see over here, there's actually one right here. This person is getting thrown over by this person over here. But let me get rid of that. Okay, I'm gonna show you a video, and this video would be right here. Okay, this is a Uchimata, and this throw works like a crowbar, where your leg is a lever and your hip is the fulcrum. The trick is positioning your body in the right place. If you don't, and if you're just an inch off the placement of your thigh and hip, the energy doubles for throwing your opponent. And if you perform it correctly, Uchimata is the type of move that takedown that requires almost no energy, yet it can deliver up to 5,000 pounds of force. And that is it. Okay, moving on. We will be going into this. Okay, so now let's take a look at this figure over here. As we see, there's a figure right over here with these people fighting each other. And let's look at this as a two-body problem. First, we will conserve momentum of the attacker, which is m1, and the defender, which is m2. M1 is the attacker, m2 is the defender, and the equation will be this: P1 equals M1 V1 and P2 equals M2 V2. Now, if we say that the M1 strike M2 head-on over a certain time, we would find that the force of the interaction is in this. We will find the force through this equation. That's what I'm trying to say. And by subbing in the numbers that if we have any values, if we add them to these variables, we're going to get a force that is probably going to be, a devastating amount of force. And the pressure, of course, again, we will be using this pressure force. That's F over A, because we will get the force right here, and the A is going to be the, the distance of the person that's going to attack him with his fist or attack him head on. But let's just say this devastating force and the pressure that would be exerted on M2 if M1 were to strike head on with a fist, because let's not forget M1 is the attacker. But let's say, so by avoiding the head on attack with a small step back, so if M2 dodged the attack and used his rotated his body and grabbed him, as we see right here, this person attacks him and he dodges and grabs him from behind, rotating the body at an angle to the attack and then blending with the attacker to create an inelastic collision. We not only conserve the momentum of and energy, but add to it, and by adding our own mass and velocity to the motion of the attacker and use it against him, we will be able to use more force to throw him, as shown in the second part of the figure over here. This person gets him and throws him on the ground. But for that, we can use this equation right here. L equals R multiplied P equals PR sine theta. That's supposed to be theta. I don't know why I turned it to Q. That is supposed to be theta. But for aphorisms, we will let theta be 90, so that L equals PR, which equals to MVR, where M will be the combined mass of the attacker, V is the velocity of the two person as a system, because they're together now, and R will be the average distance of the attacker's body as it separates from the defender's body during rotation. And for this portion, the attacker's head and upper body will be pulled tightly into the defender's chest. This allows the attacker's lower body to drift outward from the defender as they rotate. You can see in the picture, above that the attacker comes in, defender steps at an angle and pulls the attacker in a rotation, which causes the attacker to fall, as in a takedown, where the person will take him down and throw him on the ground over here. And you must understand that in soft style, the initial velocity of the attacker dictates that the velocity of the rotation. So this is not so much for reasons of physics, but for a reason of maintaining the flow of the movement. This is to minimize the energy output required on the part of the defender. Just saying. I'm just saying that part just for a heads up.